Last time we talked about constructive, destructive interference. We talked about looking at a wave and being able to determine the wavelength, amplitude, frequency, all of that stuff. So now we can take everything that we've already talked about and go one step further. And that's how we get standing waves and the concept of resonance. So we already talked about wave interference. So here we have two waves. We have this red one on the left and the blue one on the right. These waves, when you put them on top of each other, or as they pass each other, that's called the principle of superposition, where you are basically combining your waves and you are resulted in either constructive or destructive interference. So, as these two waves come towards each other, and you see that you have this blue pulse on the top, the red pulse on the bottom. Well, obviously, if those two pulses are going to be on opposite sides of each other, meaning one is positive, one is negative, you know that when they combine, they should essentially cancel each other out because you have a positive and a negative. And that would result in looking like this, where you can literally see like the exact image just simplified. So this solid line right in the middle here, this on the zero, representing a zero amplitude, is the result of the destructive interference of both of these wave pulses. As these waves continue towards each other, you end up with a situation like this, where now you have your two wave pulses that are going to be directly on top of each other. So this one on the top, this positive, with the positive amplitude, will add together to give you a greater amplitude. The ones on the bottom will constructively interfere, but in the negative direction. So that's how you get this negative greater amplitude. Remember, this is just like a snapshot of what's happening as the waves are passing each other. They don't just stop, and you don't see them like this, they don't stop for like a second. They just continue. So you see this like continuous motion, but this is just broken down so that you are able to see. So then this wave will continue. Let me go back. It will continue, and it will just continue to pass each other. And the blue wave will end up on the left continuing. The red wave will end up on the right continuing. And it will act as if nothing ever happened. But we know that they were superimposed at one point. So now we look at this picture here. This diagram below represents two waves traveling simultaneously in the same medium. At which of the given points will maximum constructive interference occur? Well, if you look at letter A does have some parts of the positive direction that are going to overlap. So does letter C. There's really no difference between A and C. So we know that that cannot be maximum constructive. It will be some constructive, but just not maximum. If we look at letter B has some of a crest and some of a trough in a positive and negative direction. And we know that if you have a crest and a trough, then that means that you're going to destructively interfere. So B is not correct either. If you look at letter D, maximum constructive interference means that you're going to have your maximum amount of amplitude possible. And the question is, does not specify positive or negative. So if we're looking at letter D, you will have maximum negative constructive interference, but it's maximum constructive. So D should be our answer. If you look at example 2, we want to draw a new wave based on the superposition of waves A and B. So the first thing that we do when we look here, we look to see the wavelengths. And if you look at these waves, both waves have a wavelength that is equal to 1 meter. And you know that because you start at 0. You have one pulse, that's 0.5, another pulse, that's another 0.5. In order to have one wavelength, you need two complete pulses. So I have one whole wave that takes up 1 meter, a half a wave that goes to 1.5. So I know that I have 1.5 total wavelengths in this picture. The frequency is also the same, meaning that you have 1.5 wavelengths in both diagrams. So we want to combine these two to give us our new picture. If you look at wave A, it has an amplitude of 0.2 meters. Wave B has an amplitude of 0.1 meters. And because we know that if we literally take A and put it on top of B, you're going to have maximum constructive interference at in both pictures, we know that our new wave should have the same wavelength, same frequency, but its amplitude should now be 0.3 meters all the way through because it is going to have maximum constructive interference at all points. So now we can look at these waves rather than look at them like front as we've been looking at them. We can look at them as if we are like standing on top of them and looking what's happening as these waves are coming towards each other. One thing that you need to make sure that you realize is that these waves are spherical in shape, which means that they're circles, which is why you have a circular shape here. As you speak, you have these curved sound waves that are coming out from your mouth. Those waves are not just like perfect static horizontal lines that are coming out. They are curving and they're going around, which is why people are able to hear you all the way around you, not just if you're standing directly in front of somebody. So these kind of pictures, you'll always have some type of key. In this case, you see that you have a crest, which is a solid line, and a trough that is a dashed line. So we can look at it like this. This should look very familiar to you, like if you have, like if you drop a rock in water or something like that. You'll see an exact picture that looks like this. So the first one that we look at is this little dot right here, where you have two dashed lines that are going to come towards each other. Here you have two troughs, and if two troughs meet, we know that if the two of the same pulses meet, we will have constructive interference. If you look at this one on the bottom, we have two solid lines that interfere, and those are two crests. Again, if you have two of the same pulses that interfere, you will have constructive interference. Now, if you look at a position where you have a dashed and a solid line, so a trough and a crest that interfere, well, now you have two opposite pulses, and that's going to result in destructive interference. So if you have two of the same pulses, they constructively interfere. Two opposite, meaning a crest and a trough, they will destructively interfere. So this is what we call a standing wave, and a standing wave is a result of reflection and interference working together that results in a standing wave. So the first thing that we need to understand when we're talking about a standing wave is that you have two fixed points on either end of your wave, meaning that you have, whether it's a string that is connected to two hooks on either side, or two people holding a jump rope on either side, or two string, or a string that is fixed to, I don't know, glued or held or taped or nailed, whatever it may be. These two ends of your rope or slinky or whatever is making up this wave is fixed, meaning that they cannot move. So that's what's happening on both ends. The other thing that you need to realize is that you are reflecting, right? So this is like, you could literally, looking at this picture, you can visualize a jump rope. So you have a jump rope that's going up and down, up and down. And if you do it pretty fast, it almost looks as if there's more than one rope there that's creating this reflection that you see because it's going very fast. And our eyes cannot process that, the difference between them, because they're just looking like it's two separate pieces. But we know that there's really only one wave or one string that's there. So we have reflection, meaning that this wave will travel down its medium and then come back. And we have interference, because we know that as this wave is traveling, you have this interfering of constructive and destructive positions. So standing waves contain a pattern of nodes and antinodes. A node is at maximum destructive interference. And if you look at this picture, you see that a node is all the way along your equilibrium line. It's all the points that are along your equilibrium line. An antinode represents your crest or your trough that is made from the one wave itself, the original wave. So an antinode is at your crest and your trough. A node is all of the points along your equilibrium position. So nodes, again, are stationary points. We'll talk about what it means to be in and out of phase in a little while. Antinodes have your maximum displacement. They have your amplitudes. The node will have an amplitude of 0. An antinode will have your maximum amplitude, depending on what it is for each particular wave. So here's a picture, and this is the way that you're going to see them in questions. So this says, how many nodes are represented in the standing wave diagram? So you literally go through and you count all positions along your equilibrium position, including your two end points. So if you look here, we have one node at the end, another node right here, another node right here, and a fourth node at the other side. So all of the points that are along the middle line here, draw it in if you don't see it, are nodes, which means that we have 4 nodes along your equilibrium, or 4 nodes in the standing wave diagram. Now, the question doesn't ask this, but let's talk about it. What if the question asked you how many antinodes there are? Well, like I said, this looks like there are 2 separate waves or 2 separate strings that are acting here. We know that that's not true. We know that a wave itself vibrates. A wave has reflection and interference, or a standing wave for that matter. So when you look at these pictures, even though it looks like there's 2 waves, there's really only one, because we know that it is a reflected wave that is also shown. So when we're talking about a standing wave in this kind of picture, and when they ask you about antinodes, you are only looking at one of those strings, always. So if you want to know an antinode, you just look at one string and you look to see how many crests or troughs make up that one string. So here's 1, 2, 3 antinodes. So in this picture, you have 3 antinodes and 4 nodes. The last thing that we're going to talk about today is something that is called resonance, the concept of resonance. Resonance is a really interesting phenomenon in physics. It's very cool, and one of the things that I love to do when talking about resonance is show you some really interesting videos that has to do with resonance. And I actually posted them. I posted them in Google Classroom for you, so definitely check them out. We will talk about them together when we review. But resonance itself occurs when a medium is vibrated near its natural frequency. So every single object, everything, has its own natural frequency. And in order to find out what its natural frequency is, you literally go over to whatever object it is and flick it. So like if you go over and you take your, your phone, so I'm holding my phone, and if you flick it, you hear that. That's a very low pitch, a very, very low tone. That's its natural frequency. If I have this can in front of me here, that's a much different tone. That's its own natural frequency. So anything that you have, you just go over and kind of just like flick it with your nail, and that pitch that you hear is the natural frequency of the object. So when you are able to vibrate near a natural frequency or create a tone near to match a natural frequency of an object, you are going to create constructive interference. As these 2 waves are going to interact, you have constructive interference. That's going to be too much energy, too much amplitude for that object to handle, and that's when it explodes or breaks or collapses. So constructive interference occurs, again, you have an extremely high degree of this energy that causes these very large vibrations. And again, it's too much for this object to handle, so it will be destroyed. If the If the vibration has enough energy and the correct frequency, again, matching the frequency of that object, the medium may be damaged or destroyed. And I included those videos. Definitely check them out, and we will talk about it when we review.